Hi, everybody. Welcome to today's AZ Water webinar on microplastics. My name is Gretchen Baumgartner, and I'm the chair of the leadership committee, and I'm the sponsorship coordinator for the conference committee. It's my pleasure today to introduce you to today's topics and speakers. This webinar is part of an extension of the 2020 AZ Water virtual conference, and its presenters and organization are one of AZ Water's platinum level conference sponsors. Without the sponsors like Carollo, this conference wouldn't be as successful as it is. With that, I would like to introduce our moderator for this webinar. Welcome Jessica Dressang of Carollo Engineers.
Thank you, Gretchen. Good afternoon, everyone, and thank you for joining us, and thank you to AZ Water for the opportunity to share our insight on this topic with a large audience. Some logistics here. This is a Microsoft Teams live event. Your microphone and webcams are automatically muted when you join, but you can ask questions at any time using the Q&A window, which you will find in your toolbar, and we will have plenty of time at the end to address them. One PDH will be issued automatically to those who register for this event on the AZ Water website. Many of you probably already received that email indicating that. If you did not register and you would still like credit for attendance, please reach out to Shayna at staff@azwater.org or to Kayla and I. Our contact information will be provided at the end of today's presentation, and we can certainly help you out. Now on to the presentation, microplastics from mystery to monitoring and mitigation. I'm excited to introduce Kayla Cook. Kayla holds a Bachelor of Science in Environmental Engineering from Mississippi State and a Master of Science in Environmental Engineering from Arizona State University. She provides leadership in Carollo's microplastic strategic initiatives and focuses on study and design in water and wastewater treatment and infrastructure for municipal clients. Please welcome Kayla.
Thank you so much, Jessica. I'm really excited to speak with you guys today about microplastics in water and wastewater treatment. First, we're going to start talking about why are microplastics an issue. Then we're going to go into regulations. We're going to identify some key regulatory challenges, current and anticipated regional and national regulations for microplastics and plastic-associated additives. And then we're going to go into water and wastewater treatment plant concerns, monitoring, and mitigation. We'll discuss briefly the impacts and concerns for microplastics in treatment processes. We'll also discuss removal technologies, including traditional and emerging. Lastly, we'll talk about some key elements to a successful monitoring campaign for microplastics. First, why are microplastics an issue? Well, let's define what a microplastic is. Microplastics, or plastic litter in general, is actually typically defined by the size range that it occurs at, beginning with macroplastics. So we have a macro, meso, micro, and nanoplastic with size ranges as noted on the screen. Mesoplastics and macroplastics can degrade into micro and nanoplastics. Microplastics are also referred to as large and small, whereas nanoplastics can be referred to as submicron and nano. The California State Water Resources Control Board defined microplastics with a blanketed term. So any plastic particle between 5 millimeters and 1 nanometer is within the microplastic category. For the remainder of this presentation, I will refer to microplastics and nanoplastics collectively as microplastics simply. Additionally, there are other non-defining criteria to describe microplastics, including if they are produced in that size range or if they degrade from larger plastics into that size range are secondary microplastics. So why are microplastics an issue? First, plastic is everywhere. It's in our rivers, oceans, streams. It's in our rainfall and remote regions. Unfortunately, it's also in our food that we eat. Shellfish, fish, sea salt, bottled water, and tap water, just to name a few. There's a possibility that microplastics and nanoplastics could also be present in agricultural crops and sugar. We'll talk a little bit more about why this is possible, and this isn't 100% confirmed yet. Lastly, microplastics are in the human body. of the individuals studied, 100% of people excreted microplastics regardless of their diet. That includes vegetarian and vegan individuals as well. And 78% of US EPA's priority pollutants are associated with microplastic pollution at many orders of magnitude higher than they're found in the environment. The key word here is actually associated, because microplastics or plastics in general could actually be synthesized with some of these priority pollutants as well. As a plastic particle degrades in the environment, its possibility to leach additives actually increases, according to some studies. So how are microplastics occurring in the environment? Well, if we begin with the public and the consumption of microplastics here, we're exposed possibly through produce, as I mentioned, definitely through our seafood and our shellfish, and definitely through our bottled water and our tap water. Bottled water consistently has higher concentrations of microplastics than tap water. After we consume these particles, we are known to excrete some of them or all of them. The partitioning within the human body is unknown. Additionally, as we're washing our clothes, in our washing machine, effluent is actually a large amount of microfibers. These could be synthetic, semi-synthetic, or of course natural fibers. The synthetic and semi-synthetic ones are primarily the concern that we have here. After consuming microplastics and releasing microfibers, this wastewater then goes to a wastewater treatment plant where anywhere between 35% and 99.8% of microplastics can be removed. This is a concern in terms of what isn't removed then goes into our rivers and streams or general surface water bodies. What is removed, if biosolids are produced, can then be land applied. So we may be applying massive amounts of microplastics onto our agricultural soils, and these can be possibly uptaken by agricultural crops. This actually brings this full circle where we are once again consuming some of these microplastics. Additionally, with rainfall, microplastics can then occur in runoff into our rivers and streams or general surface water bodies, and this increases that concentration in the environment. As we then use surface water potentially, or even some groundwater has microplastics in small amounts to treat our drinking water. I think this is important to view microplastics as part of the water cycle and how this is very full circle. Are microplastics toxic? Well, I'd like to think of this as a three-pronged approach to toxicity, where you have the physical or inherent particle toxicity, the release of absorbed contaminants, and the biological communities that can grow upon microplastics. The physical or inherent toxicity research actually, in some cases, goes back decades on polymeric joints. Polymeric joints can release microplastics, causing osteolysis or bone resorption and osteomyelitis or bone cancer. Additionally, the inhalation of microfibers is associated with interstitial lung disease. So these impacts are very well known. However, these are different exposure routes than would be present through drinking water. Additionally, physical or inherent particle toxicity increases as the particle decreases in size. These various impacts in literature of consumed microplastics can possibly include neurotoxicity and local necrosis if deposited in tissue. Next, the release of absorbed contaminants can be a major concern for microplastics. As I previously mentioned, microplastics are associated with 78% of the EPA's priority pollutants. This includes PCBs, triclosan, DDT, pharmaceuticals, and PFAS. PFAS in particular can be used as a coating on clothing and then released with microfibers. Lastly, biological communities can be a concern here. These include microorganisms related to septicemia, antibiotic-resistant bacteria, and the concern that plastic can act as a raft in the environment for invasive species. This is confirmed in literature. Next, let's talk about the current and future regulations and the associated challenges of microplastics. What are the regulatory challenges? Well, first, there's no standardized method. You begin here with extraction, which is used to gather your sample, followed by processing to remove organic matter or sort your sample, and then identification to verify the material is truly plastic. There's no standardization for this yet. However, ASTMs will be released soon to support this. The second concern here is, what are those? How do we define microplastics? Defining and non-defining criteria were actually spearheaded by the California State Water Resources Control Board. These defining criteria include sizes and varying degrees of synthetic material. However, morphology such as fiber, fragment, or film are not, in fact, a defining criteria. The third concern here would be, are these particles toxic? We discussed some of the potential pathways or impacts for microplastics on aquatic species or the human bodies. These are not yet truly confirmed, nor has the scientific community reached consensus. So this piece here remains uncertain. For current and anticipated microplastic regulations, in 2015, this began with the Microbead-Free Waters Act in the United States. Of 192 countries studied, only 8 of these countries banned microbeads. Next, in 2018, California passed the Safe Drinking Water Act focused on microplastics, or State Bill 1422. State Bill 1422 is one of the things that I will reference here in this presentation because it did spearhead this challenge of microplastic contamination in drinking water. In 2020, earlier this year, the definition of microplastics was approved, and beginning next year, this definition will then move into an implementation period for monitoring microplastics statewide in drinking water. Another challenge associated with microplastics is that there's various nomenclature here, and these are microplastics can be frequently referred to as myrtles, microbeads, pellets, or even microfibers. It's important that we utilize the same terminology when we reference these subclassifications. Also here, I've listed polymer under the oil and gas industry because polymers are typically synthesized by oil and gas companies. One of the interesting things here is that last year, the San Antonio Bay estuarine waterkeeper won a case against Formosa Plastic for $50 million due to the release of what was termed nurdles, or pellets. These are in fact microplastics as well, just by a different name. For plastic and plastic associated additives, there are already existing primary MCLs. These include monomers and various types of flame retardants, colorants. These contaminants are utilized to either synthesize plastic or are leached from microplastics. Early research indicates that microplastics leach at higher rates than macro and mesoplastics due to possibly the surface area to volume ratio. Some of the monomers here include acrylamide, styrene, vinyl chloride. Additives include DEHP, biocides including arsenic, which is found in PVC. Cadmium and lead are degradation products for heat stabilizers. Dioxin and cyanide are released from PVC, and chromium and PCBs are pigments for plastic products. The topic of microplastics in agricultural soils and crops is all over the news. This is something the public is becoming increasingly aware of, and we need to have this on our radar as an industry. Some of the key concerns here are that microplastics are detrimental to land fertility, and they will be difficult to regulate in the future if needed. Next, let's talk about water and wastewater treatment, plant microplastic concerns, monitoring, and mitigation. Microplastics are fragmented into a more toxic size range across water and wastewater treatment processes. This is a concern due to the increased toxicity of smaller particles. Additionally, some research is indicating when utilizing very robust methodologies, that some of the small microplastic size range could actually be one of the higher percentage components of microplastics in wastewater effluent and raw water, as well as drinking water effluent. I did a little bit of research into some of the trends of microplastic removal rates and releases. This started indicating that our removal rates are decreasing with time because of methodologies that are increasing with robustness. We know that microplastic contamination is influenced strongly by per capita dischargers in the same way that BOD and TSS typically are. However, industries can play a critical role here. Textile mills are shown to release up to 2 orders of magnitude higher microfibers in the effluent, and some of these are being quantified more now as well. These numbers that you see in front of you are only for municipal processes. Why are removal rates decreasing? As I mentioned, there was very vulnerable data early on between 2010 and 2017. 33% of studies quantified utilized visual identification only due to microscopes, using microscopes instead of more robust characterization instruments. This was actually some research that I did with Dr. Rolf Halden at Arizona State University. Some studies also indicate that small microplastics are more common. As you can see here in raw water, you have 97% up to 100% of raw water is small microplastics. In water effluent, 100% of some studies indicated small microplastics. These small microplastics are the most difficult to quantify. Data and methods are just now beginning to approach that size range near 1 micrometer and 10 micrometers. This is incredibly challenging, and that's why we wanted to talk to you guys today about recommended monitoring methods in order to create these more robust data sets. For water treatment, one concern here is the degradation or possible abrasion of macro and mesoplastics in infrastructure. 5 common polymer types were found in drinking water that are also linked to some of our infrastructure. One being tanks coated with resins, distribution mains, distribution pipe fittings, membrane filters, and coagulant aids. This degradation could occur by scratching the surfaces or aging infrastructure. One of the key challenges is that this contaminant is not visible, and as I previously mentioned, it's incredibly difficult to quantify on a small, once you approach that small microplastic and nanoplastic size range. The removal efficiency of water treatment processes varies, of course. With ozonation, I've actually placed this outside of a typical recommended process because ozonation actually creates more microplastics. One very interesting study on an advanced drinking water treatment plant determined that the number of microplastics in the effluent after ozonation increased. And these are more toxic as well because they're going to occur at a smaller size range. Here, the most recommended would be dissolved air flotation. Additionally, Dr. Gerba at the University of Arizona is researching soil aquifer treatment for microplastics, so his team will provide an update for that in the future. Additional water treatment plant concerns include disinfection. Here, microplastics are releasing dissolved organic matter, which then becomes a disinfection byproduct precursor producing trihalomethane. Additionally, disinfection can increase the hydrophobicity of microplastics and increase the absorption rates of the environmental contaminants. Following exposure to disinfection, microplastics also increase the presence of toxic chlorine and chloride bonds. Novel removal treatment methodologies are being considered here for microplastics, particularly electrocoagulation and magnetic nanoparticle enhanced extraction. Electrocoagulation removes up to 99.2% at a particular pH, and magnetic nanoparticle enhanced extraction is around 92%. For wastewater treatment, of course, you're going to utilize different unit processes, and so some of your challenges for wastewater treatment are going to be very different. While the liquid stream may efficiently remove microplastics, these most likely end up in the solid stream. This is particularly a concern for land-applied biosolids, as I previously mentioned. Concentrations increase more than twofold on wet weather days, sometimes up to eightfold, and there's a similar concern with disinfection byproducts for wastewater as well. The removal efficiency for wastewater treatment plants varies dramatically. A lot of the initial research was indicating around 99% removal for microplastics in wastewater treatment plants. This has changed with increasing accuracy of the methods. So of all of our unit processes available in wastewater treatment, membrane bioreactors are currently one of the highest. However, there is one interesting study that looked at small microplastics, and that removal rate was a good bit lower. This really highlights why a lot of the literature that we have right now really depends upon the method that was used to quantify the microplastics. Here in the liquid stream process, once again, you can have between 0.1% and up to 65% of microplastics that are in the effluent of a treatment process released in the effluent. There are activated sludge concerns that we'll talk a bit more about, and there are solid stream concerns. The activated sludge concerns include that microplastics can inhibit nitrification and improve denitrification. This isn't that surprising whenever we think about there's tons of studies on bisphenol A and its toxicity to microorganisms and the human body in general. So as microplastics release BPA or other bisphenol analogs, this can inhibit and hurt our unit processes. Additionally, studies indicate that activated sludge may increase microplastics' ability to absorb contaminants. We're looking, again at that surface roughness. For solid stabilization, drying, and anaerobic digestion, each of these unit processes actually does increase the toxicity of the particle by decreasing the particle size following treatment. This increases its potential to become airborne as well after being land applied. We are finding microplastics in the atmosphere and in rainfall, as I previously mentioned, and we don't yet truly understand some of the sources for why these are occurring, but these are important things to consider. These are important pathways to consider. Low concentrations of microplastics were actually shown to increase biogas production, while high concentrations were shown to decrease biogas production. This is once again due to bisphenol A as a bad actor there. Biosolid land application is one very key concern for microplastics in wastewater treatment plants. Studies are showing that nanoplastics can be uptaken at the root of agricultural crops. Here's a photo to the right of actual nanoplastics that were pictured on an agricultural crop. This method here actually, I believe, uses SEM-EDX or SEM-EDS, and this is considered a vulnerable method by some researchers. We're going to talk a little bit more about why it's so important to use the appropriate instrumentation to quantify microplastics. Next, microplastics, when they're land applied, actually do begin to accumulate in soil over time. This leads to decreased microbial activity, and nanoplastics in particular can be directly toxic to roots. It also increases the soil bulk density, which decreases the ability for soil to absorb water. I previously mentioned the microplastic identification process that begins with extraction and processing. Particularly in wastewater treatment plants, the amount of organic matter and sediment that's present leads to the need for a very robust method. Quality assurance and quality control are perhaps the most important pieces of a microplastic monitoring plan. Recent studies even show that the material of gloves can cause contamination. Also, ambient air, we know microplastics occur in the air, and so we have to consider that. We have to always maintain procedural lengths. Also, it's recommended to not use any plastic whatsoever whenever you're collecting your sample. This is a genuine challenge today. So you have to use glass containers. You need to rinse your containers with DI water, because if they've been sitting out in the open, then they can have microplastics or microfibers fall into them, essentially from our ambient indoor air even. And then you want to cover it with a non-synthetic material. Additionally, wearing cotton lab coats, cotton clothing will reduce that contamination amount. These are actually some photos that we've taken at our Water Arc lab when working to quantify microplastics. The first key piece here is the extraction phase of a microplastic study. Of all of, between filtering, screening, and bulk sample removal, the most recommended here would be a composite sample. And this can be used from your current composite sampler. This is recommended because there are diurnal variations of microplastics present. And this is kind of an intuitive concept. If you think about, some people wash their clothes at certain times of day, and microfibers are one of the huge contributors to microplastics in wastewater in particular. Following the extraction, the processing phase begins. Here you will want to oxidize or remove all of the organic matter and biofilms on the microplastics or around the microplastics. This is typically done with peroxide and Fenton's reagent. This will take a good bit of time and multiple steps typically to truly remove all of the organic matter and the biofilms off of the microplastics. Additionally, if you have a very densely organic sample, then we would recommend density separation here just to remove this sediment. I talked a little bit previously about some of our identification challenges, where spectroscopy and spectrometry can't identify the material composition of plastic. However, microscopes cannot verify the composition, and they can only interrogate the exterior. This is part of why we would primarily recommend micro-FTIR or micro-Raman for the quantification of microplastics. There are other methods, including pyrolysis GCMS. However, this actually determines a mass of microplastics and will not give you a quantity. Mass loading in the future could be our primary way of measuring microplastic contamination. However, this is not yet a standardized method either. Are we quantifying the most toxic particle sizes? Research that I did with Dr. Rolf Halden at ASU indicated that it doesn't seem like we are. Here you see that around the average microplastic that was quantified was closer to 300 micrometers, but we know that these get more and more toxic as they get smaller. Around 100 micrometers, typically microplastics can be found in the blood, urine, and cerebrospinal fluid of different organisms studied. And they also deposit in the liver, kidney, and gut at even smaller size ranges. This is part of why it's so important that we quantify even the smallest microplastics that we can and approach that methodology limitation. There's a lot of research happening at different Arizona universities, including Arizona State University and the University of Arizona. Let's talk a little bit about what's happening over there. Dr. Rolf Halden, as I previously mentioned, has a lot of research going on with the Center of Environmental Health Engineering. He's previously published with his team methods for detection for microplastics and nanoplastics in human tissue. Additionally, research on the chemical and physical changes of microplastics during chlorination are pretty key studies that have been done already. And the nationwide mass inventory and degradation of plastic contact lenses in wastewater was done as well there. At the University of Arizona, Dr. Chuck Gerba is researching soil aquifer treatment for microplastics. This is an ongoing study, and it is in collaboration with Pima County. So I'm very excited to see some of the results in the future for that study. He has looked into plastic in other ways, including a study on the inactivation of bacteriophages and poliovirus in plastic water pipes. Some of our key takeaways today include what the challenges for microplastic regulation are. First, the lack of standardized methodology. The production of ASTMs in the future will be really critical to addressing this. Second, the confusing nomenclature and how we define microplastics. The California State Water Resources Control Board did adopt a very robust definition of microplastics that includes nanoplastics. And it defines microplastics in such a way that even 1% of synthetic material can be considered a microplastic. Third, the undefined toxicity, and this question remains uncertain. Concerns for microplastics in water and wastewater treatment plants includes fragmentation of microplastics into nanoplastics and becoming more toxic there, the release of microplastics possibly from infrastructure, and the inhibition of nitrification biogas production. Also, releasing disinfection byproduct precursors is a major concern, and last but not least, the accumulation of microplastics in soil and agricultural crops potentially is an incredible challenge with wastewater, sludge, and biosolids. To kind of begin approaching these problems and begin looking for solutions, we need to monitor. We need to quantify the number of microplastics in our treatment plants and in our effluents. And successful monitoring, as I previously mentioned, it includes a thorough QA/QC checklist. We would recommend composite sampling due to these diurnal variations and seasonal variations and spectroscopic analysis. So I'm going to hand it back over to Jessica here to finish up the presentation.
Great, thank you, Kayla. For more information or inquiries, we'd love to hear from you. You may reach out to Kayla or myself or any of our 3 Arizona Carollo offices through the contact information we have shared here. We'll now move on to our question and discussion session here, Q&A. Feel free to continue to ask questions using the Q&A window found here on your toolbar. I will get into these now. The first question that's been asked a few times is, will the presentation be available afterward? And the answer there is yes. AZ Water will be, we've been recording this presentation and it will be published on AZ Water's YouTube channel. So look for that afterwards. And we will also have a PDF of the presentation available, and we'll work with AZ Water to distribute that to attendees afterward. The next logistical question is, are PDHs available for this webinar? And one PDH is available for those that officially registered through the AZ Water event page. You should have received an email indicating that that would be on its way after the presentation automatically. If you're, say, in a group setting here watching this presentation today, or you receive the link in another manner outside of AZ Water, please feel free to contact me or with my information, jdresang@carollo.com, and I'll type it here in the chat as well. Or you can reach out to staff at azwater.org, and they can work with you to provide you that PDH. We'll jump into a technical question. This one is regarding ammonia effluent limits. So with ammonia effluent limits getting more stringent, the statement on nitrification inhibition can be a real issue. Is there some indication by what percentage nitrification can be inhibited in the bioreactor? Is there a recommended operational target?
That's a really great question. There are actual values in studies for the amount that microplastics inhibit nitrification. So I would recommend to check in literature for that value. It is pretty noteworthy. I believe it's higher than 30% there.
Great, thank you. Could you elaborate a bit more on what regulatory actions will be in California? Do we know yet? Do you have an idea, or even just some thoughts?
Well, the previous work that the State Water Resources Control Board has done looks at what the definition is, that they spent an entire year on defining microplastics there. And this includes a long list, of course, of different polymers and copolymers, up to 1% synthetic material. So most likely what you're wearing right now, if you wash it, it releases microfibers. It's probably going to be semi-synthetic at least. So it's an incredibly broad definition, and moving forward from the definition, currently the Southern California Coastal Water Research Project, or SWRP as they're known, is looking into methodologies for microplastic quantification to provide that intercalibration data to the water board. Carollo is on this study to look at intercalibration and microplastics methodologies. And moving forward, it really seems like the methods that will be implemented will be some type of micro FTIR, micro Raman, as I previously mentioned. These are the more robust methods available currently, and pyrolysis GCMS may be on that list. With these methodologies, there will also be the release of multiple ASTMs that will help us be able to truly quantify microplastics and look into our different extraction, processing, and identification methods. I believe in 2025, or I'm sorry, in 2021, there will be a implementation period where statewide there will be quantification and implemented methods to monitor for microplastics. And then in 2025, that entire phase will be reiterated, going back to health-based guidance for the definition of what a microplastic is.
Great, thank you. The question said, I might have missed it, but do you know of any standards that are being developed for, one, the definitions of microplastics, and or two, quantification or analysis? I know you touched on that kind of earlier on. Maybe just a little bit of a recap there.
So modification or analysis to the definition, or modification to the definition, I guess I'm a little confused by the question.
Sorry, it just says, do you know of any standards that are being developed?
Yes.
With definitions.
Yes. So I think that the definition that California's produced will be adopted by other regulatory agencies. It was a huge challenge, and I would be surprised if other regulatory agencies go through that entire process again, actually, because to determine the definition of microplastics, it is an incredible challenge. As I previously mentioned, there's all of these different subclassifications, there's all of these different size ranges. In terms of methodologies, the ASTMs that will be released should provide ample guidance for quantifying these particles in the environment and in water and wastewater treatment plants.
Great. Thank you. Do you know if there are any commercial labs that are currently testing for microplastics other than at the university level?
There are labs that are testing for microplastics. Eurofins, of course, is testing for microplastics currently, and Carollo can do a few microplastic samples. We would recommend to work with someone on your sampling and your monitoring plan here, because there are these noteworthy challenges associated with even extraction of microplastics and not contaminating your sample there.
Great. Question here is whether a focus on car tire wear as a contributing factor to microplastics has been considered. And if yes, could a natural ingredient as a good substitute be used going forward?
Ooh, that's a big question. Like, you know, redesigning our car tires. Well, I know that I've seen something interesting about a device that can capture microplastics from car tires. It is a noteworthy contributor to microplastics in stormwater. So we do want to start looking at different novel, potentially, solutions for capturing microplastics before they occur in our environment, in our drinking water, etc. And there's the novel solution to microplastics from tire degradation that captures them before they're released. There's some other novel solutions for microfibers in washing machines that aim to capture your microfibers before they even go to your wastewater treatment plant.
Thank you. Are high-risk industries, for example, textiles, recognizing the issue, and is there a trend towards effluent treatment at the source?
Absolutely. They have absolutely recognized this. There's multiple consortiums available to be able to get involved in this, particularly the Microfiber Consortium is really looking into the challenge. The textile industry itself is producing guidelines to reduce possibly, you know, and continue reducing possibly down to zero the number of microfibers in effluent. I know of some textile companies that are actually looking into their treatment streams and how they can further reduce this. So it is absolutely something that the textile industry is looking into, and they want to be ahead of before it becomes a more noteworthy challenge to remove microfibers from the environment or from drinking water resources.
Great. Has a best sampling method for surface water collection of so what is the best sampling method for surface water collection in microplastics? Long-term samplers? Question mark.
There aren't that many long-term studies on microplastics. There's in surface water bodies. There's one that I know of that hasn't been released yet. But yes, I would recommend studying something long-term because we know macro and mesoplastics degrade into micro and nano. It would be very interesting to be able to confirm that microplastics are in fact increasing in the environment and in different surface water bodies over time. And I'm not quite sure about the recommended sampling method there. There are various methods that I previously mentioned, including sieving and filtering, are using different types of nets. This one key element here, and I had a recent conversation with a guy at USGS that's very knowledgeable on this topic, and he finds it incredibly important that people sample the entire water column because the top of the water column will only really contain floating microplastics, and then you're going to have a lot of the more dense microplastics settle to the bottom, such as PVC possibly, and PVC is one of the most toxic plastics available just in general to the human body, to aquatic organisms, etc.
All right. So looking at where we are at and maybe your crystal ball or longer term, are we on the, what are your thoughts? Are we on the trajectory for elimination or learning how to live with microplastics? How realistic is a future of eliminating microplastics from the environment?
I think the pivot point there, or the fork in the road, will be when we determine how toxic microplastics are to the human body. This is incredibly important. If they are as toxic as some studies are suggesting due to accumulation in the liver, kidney, and gut type of things, or neurotoxicity, then I could definitely see us providing multiple mitigation strategies, and mitigation strategies will be critical moving ahead if that's determined. If it's determined that microplastics are not much of a problem for human health, then maybe we'll begin to look at different methods for reducing them in the environment, because we do know that they are pretty toxic to different aquatic species, depending on the type of species.
Great. Looking back into treatment, why does reverse osmosis perform so poorly? Any additional thoughts there?
I've wondered the same thing myself. Typically, what early studies were showing is that microplastic removal was based off of size exclusion. But that was a really interesting study. And I think that we really need more data points at this point in time. I want to point back to, getting these ASTMs, getting some really robust data, and then looking at, once we have the standardized method, and then comparing apples to apples instead of apples to oranges. While the data is, relatively representative at the current moment, I do think that looking more into why microplastics aren't being removed as well in reverse osmosis is a really key thing moving forward.
Great, thank you. Do you think it is reasonable to include nanoplastics in the definition of microplastics, since with smaller sizes, the properties become significantly different?
I do think that it is important to include nanoplastics. That's a really great question, honestly, because nanoplastics are potentially more toxic than microplastics are. And if we look into the fact that macro, meso, and microplastics eventually degrade into nanoplastics, then we're going to have increasing concentrations of these very small particles in the environment unless they're uptaken or deposited in soil or sediment. There's a lot of microplastics in deep ocean sediment. But I do think that it's important to consider these. There was one interesting paper that I found on the release of plastic-associated additives such as bisphenol A, increasing as the particle size decreases. There are other key elements to why nanoplastics are so important, primarily though just based on how particles move around in the human body, I would say.
Great. Another question on sampling. You've recommended composite sampling for microplastics. Would that be manual or automatic? Thoughts there? And part two is, would water come in contact with plastic within the automatic composite sampler?
Another good question, yeah. So it's recommended to use stainless steel tubing in your samplers. This is not very common, and so that is one thing to look into. How much does these plastic tubes actually contaminate the sample that you're collecting? We want to reduce the exposure to plastic in every single way that we can along that continuum. And then once we're looking at composite samples, I would recommend either flow-based or time interval-based sampling. And that's mostly because we know it's diurnal, and we know the morphologies vary by time, so we want to get a truly representative sample. We don't want to just capture one moment in time if we do a grab sample there.
Great, thank you. That looks to be the extent of the questions we've received today. We really appreciate it. Lots of really great questions, whether it's about definitions, potential regulations, sampling as well, learning that even materials of construction are a factor there. So we'll wrap up here and get all of you on with your day here. So on behalf of Carollo engineers, Kayla and myself, we'd like to thank you all again for attending our microplastics webinar, and thank you to AZ Water for this opportunity to present. We hope you all have a great day, and now I will hand things off to Gretchen for some final parting words.
Well, thanks, guys. That was really interesting. I'm a water resource person, so this isn't necessarily my wheelhouse, but Kayla, that was really interesting. I really appreciate it. I want to thank all the attendees for attending this webinar, and hopefully you guys had a really great experience. The association continues to look for ways to create value to our membership. And we hopefully that this webinar, along with all the other things we do, is something that creates value for you. I'm going to mention again PDHs, although we mentioned it several times. The PDH certificate will be emailed to you within the day or so to the email address that you used to register for this webinar. I want to extend a thank you to Carollo for putting this together and then also supporting us through your sponsorship and other partnerships with the association and the conference committee. And so I just want to thank everybody for being a part of this and have a great rest of your Wednesday. Thank you.